Hello and welcome to the virtual HERACLES course, Effects of Air Pollution and Climate Change on Cultural Heritage. What is it you're going to hear in this course? We are going to get a bit into the topics of air pollution and climate change. We're going to have a look at the 4 HERACLES test sites, and our main focus will be environmental data collection. The phenomena of degradation of buildings are complex due to the numerous factors that intervene. There are factors of natural origin, such as the sun, rain, and the freeze-thaw cycle. And in addition, we have man-made atmospheric pollution. It is not easy to distinguish the share of each factor. However, there is a consensus that man-made pollutions have greatly increased the degradation rates of buildings. These pollutants are mainly emitted by industry and agriculture, as well as by the transport sector, and they contribute to the deterioration of cultural monuments in various ways on a local scale as well as over long distance. We're going to have a look at 3 of those pollutants. Sulfur dioxide, SO2, is considered one of the main indicators of air quality. It is primarily formed from the combustion of sulfur-containing fuels. It can affect the health of people and have a negative effect on the environment. Concentrations are significantly bigger in winter than in summer because of the use or combustion of fossil fuels. Furthermore, urban and industrial regions contain higher SO2 concentrations. SO2 is a major precursor to acidic depositions, usually known as acid rain. Sulfur oxides are capable of dissolving in water to give an acidic solution, which dissolutes calcareous materials such as limestone marble. Moreover, it accelerates the corrosion of metals due to the formation of acids, for example, sulfuric acid H2SO4. The effects of acidic pollutions on calcareous stone depend very much on the immediate environment of the stone. If the stone is in an exposed position where it is regularly washed by rain, then the reaction products are washed away and the surface of the stone gradually recedes. On the other hand, however, if the stone is in a relatively sheltered position, then the reaction products accumulate and may form a dense black crust on the surface, which is also known as soiling. I have included also a web link here. Cleopatra's Needle, which is an obelisk. It was transferred from Egypt to New York in 1880, and interestingly, it was more damaged in the last 100 years than in the first 3,000 years before. Nitrogen oxides, NOx, is a collective term used to refer to oxides of nitrogen, such as nitrogen dioxide, NO2, or nitric oxide, NO. NOx occur both naturally and are also produced by human activities. The main man-made source of nitrogen oxides are the combustion of fossil fuels and some industrial processes. In comparison, the main natural source of NOx are volcanoes as well as some bacterial action within the soil. Nitrogen dioxide is soluble in water and can be oxidized within the atmosphere to form nitric acid, HNO3, which is, along with sulfuric acid, H2SO4, considered to be acid rain. Ground level ozone, O3, is a secondary pollutant generated from the reactions of primary pollutants in the atmosphere. Tropospheric or ground level ozone is formed mainly from the breakdown of NO2 into NO and oxygen. This then forms ozone in the presence of UV or sunlight. The process is reversible. Um, Concentrations of ozones are therefore a function of the concentrations of NO2, NO, and the intensity of UV. Ozone is known to be a rural pollutant because concentrations are often lower in urban areas, as the NO emissions kind of scavenge or occupy the available O3 to form NO2. In rural areas, the lack of NO2 means that the ozone molecules are not being destroyed. As the reaction needs sunlight, highest concentrations occur at midday or mid-afternoon. Also, a seasonal pattern exists within spring and summer because of the available sunlight. Ozone itself has a direct corrosive effect on natural rubber, plastic materials, textiles, paint, and surface coating. What also should be considered is the synergistic effect of O3 in combination with sulfur and nitrogen pollutants, which can then have various negative effects on metals and stone materials. Not only air pollution has a negative effect on built heritage, also climate change has a significant influence. While some effects of climate change accelerate and intensify deterioration, others delay it. As we have already heard, and as we will hear again, humidity or precipitation plays a significant role. The main climate parameters affecting cultural heritage can be grouped as temperature, water, or wind-derived. Temperature-derived parameters might be increased annual temperatures or increased summer maximums. Water-derived parameters would be flooding, prolonged rainfalls, prolonged humid or dry periods, and wind-derived parameters might be wind pressure, wind-driven particulates, or gusts. Predictions of climate change are based on climate models, which build upon studies of current climate system, including ocean, atmosphere, cryosphere, land surface, and biosphere, their interactions, and factors influencing it, such as future socioeconomic scenarios of land use and greenhouse gas emissions. A climate model is a mathematical formulation comprising the effects of all key processes active in the climate system. Its effectiveness is expressed by how well it reproduces past climate conditions. One method to assess the impact of atmospheric pollutions in combination with specific climatic parameters is the concept of dose response or damage functions. The functions are being developed for materials and objects in an attempt to predict how environmental conditions contribute to decay mechanisms. Those response functions are used to assess tolerable pollution levels and to recommend air quality target levels to minimize the negative effects. What is necessary to formulate those functions? We need information on the affected material as well as on pollution parameters and climatic parameters in order to determine the tolerable deterioration rates. Um, Based on an inventory of cultural heritage, it is then possible to generate maps which show, for example, pollution concentrations, corrosivity, soiling, or threshold exceedances for the presence as well as for possible future scenarios. Within the European Noah's Ark project, the Lipfert function has been used as a damage function to determine the erosion index of carbonate stones, with rainfall and pollutant concentrations being the variables. The interesting result of the findings from the project was that actually clean rain was the most important parameter in the function. Predictions for an increase in wetting and drying cycles lead to a concern over salt damage due to climate change. Repeated cycles of dissolution and crystallization of salts present a considerable stress on already porous materials. Following, we are going to have a look at the four HERACLES test sites. The four HERACLES test sites are located in Greece and Italy. Um, Various climatic and environmental conditions pose some threats to the four test sites, and as we will see, an abundance of humidity affects all four sites. The first excavations at Knossos were carried out in 1878. Today, the exposure to sunlight, rain, and wind, an increase in extreme weather conditions pose all threats to the build material. Moreover, human-induced activities pollute the air and need to be addressed. And the effects due to humidity are numerous, as you can see here. The Venetian fortress Castello a Mare or Rocca a Mare is situated at the edge of the northwest breakwater of the Venetian harbor in the city of Heraklion. It faces adverse effects of climate change, for most significant impact from the sea. Strong sea waves have constantly been causing damage to the built material and the foundation. Again, we have human-induced air pollution, which is affecting the fortress too. And humidity not only poses a threat to the build material, but also leads to corrosion. And the two other sites, which are located in Gubbio. Gubbio is situated in the province of Perugia. It represents a historical monumental town well preserved with a long history. Due to its vicinity to a river and the surrounding mountains, the town was a point of attraction, reasonably secured from extreme weather situations and, back at the time, hostile attacks. Nowadays, mostly hydrogeological risks, intensified due to a changing climate, endanger the town, while increased torrential rains and humid soils present one danger. Buildings and structures in the old town of Gubbio suffer from the effects due to climate change coupled with air pollution. The chosen test sites are the Palazzo Gubbio, located in the center, and the Gubbio town walls. Following, we are going to get into the core of this presentation, environmental data collection. The questions we are going to answer are: why do we collect environmental and climatic data? What kind of data are we collecting for the HERACLES project? And how do we access and visualize data? So, why do we collect environmental and climatic data? On the one hand, the effectiveness of models, how well they forecast the future climates, depends on the input of historic data and is verified through the reproduction of past climate conditions. This is one reason why we collect data. On the other hand, we collect climate data to correlate climatic conditions to negative effects on cultural heritage. In other words, we collect evidence of climate change effects on cultural heritage due to persistent adverse conditions such as droughts and a growing number of extreme weather conditions like flash floodings, intense precipitation, wind bursts, etc. This enables us to formulate or define climate-related effect indicators and or damage functions, which once applied to the to climate predictions can give us the magnitude of the incoming risk for historical buildings, both in short and medium or long terms. What data do we collect for Heracles? In terms of type of data, we can distinguish the scale of data, namely global or local data, and likewise we can distinguish the data source, data from Earth observation systems, or data from ground measurements. Data from EO or Earth observation systems are available from MODIS, OMI, and Hydra Estimator. MODIS, or the Moderate Resolution Imaging Spectral Radiometer, is an instrument aboard the Terra and Aqua satellites. It provides us data for land surface temperature, relative humidity, air temperature, and aerosol optical thickness. OMI, the ozone monitoring instrument aboard ALVA, monitors ozone and other trace gases and provides us SO2 and NO2 values for Heracles. And the Hydra estimator uses data from geostationary satellites to estimate rainfall rates on a global scale. Ground measurement stations in and around the two test sites of Gubbio and Heraklion record various parameters for the project. There are 5 stations located in and around the site of Heraklion in Greece, and 6 in and around the site of Gubbio, Italy. The scope of the meteorological stations is to assess the local climate conditions and phenomena, and hence estimate the impact on cultural heritage and built environments. How do we access and visualize the data? We access ground measurement data via PSQL. The figure you see here shows the structure of the database. It has quite a simple design containing three tables: products, measurements, and stations. To give you an idea, to show you some examples of potential database queries, We're going to watch a short video which I have prepared. We are connected to our server and are able to see the three tables, products, measurements, and stations, and their corresponding columns. We're going to see some example queries now. The first query lists all measured values for all available stations recorded on one day, the 8th of July 2017. The output we are seeing consists of the time, the station IDs, the recorded parameters, and the corresponding values. An example column could contain the following information: the maximum temperature measured by the station Heraklion port on July 8th was 29.8 degrees Celsius. The second query lists all measured values for one specific station for one day, the 6th of July 2017. Station ID 5 corresponds to Heraklion West, and we see the recorded parameters and their corresponding values. The result of the third query is a list of values recorded on one day, July 6, 2017, from the station Heraklion West, including a descriptive name of the recorded product, for example, rain, high wind speed, mean temperature. And the last query lists the recorded values for a specific product, from all stations which recorded that product over a period of 3 days. So the output contains recorded maximum temperature values from the 4 ground measurement stations in and around Heraklion for the period of July 5th to July 7th, 2017. All right. How can we access Earth observation data? We can access EO data using the Open Geospatial Consortium's web coverage service or geographic user interface. For both, I have prepared a video which we're going to watch. What is WCS? WCS provides an interface to request the raster source of a geospatial image. It allows complex querying and enables clients to select and extract just a portion of the information they need. What we are going to do is we're going to access the data on 2 different servers. One is our own, the other one is an Amazon Web Services server. First, to list the available collections on the Amazon server, we submit a get capabilities request. Get capabilities generates a list of data on the server. And as we can see, we have some OMI and MODIS data on the Amazon server. In order to retrieve specific collection information, we submit a describe coverage request, which returns additional information about a collection. In our case, we want to get additional information on the hydro estimator collection. The XML output shows information such as geographical extent and other things. In order to extract data from a collection, we submit a get coverage request, a third example. The output displays a time series from January to August 2017 of precipitation values for the location of Gubbio. The coordinates correspond to the latitude and longitude of Gubbio, and the values in the list are the observed precipitation values. We can submit a get coverage request also to generate a TIFF, GeoTIFF file. The TIFF file displays accumulated precipitation values over the region of Crete on 3rd of January 2017. And as a transition to our next video, we are here able to see the same output generated using the graphical user interface. How can we visualize some EO data using a graphical user interface? We're going to use some EO data service developed by our mother company MEO, the Meteorological Environmental Earth Observation Group, in order to visualize some EO data. EO data service offers data discovery, access, subsetting, visualization, processing, and downloading services. What we're going to see in this video is a quick way of generating time series. The platform allows us to search the product catalog, and we are adding 2 products to our basket, OMI, NO2, and SO2. We load the NO2 collection into the system, and we are using the search function to zoom into HERACLES. After adding a point, we can use the plot doc to display the NO2 values. We can easily change start and end dates, and within seconds we have a time series of NO2 values for about 13 years. We can limit the extent, zoom in and out, move the displayed time frame. We're going to add a second point over Gubbio in Italy. NO2 values for the new point are automatically added to the plot. Following, we are going to load a second collection into the system. With a few clicks, we can now see an SO2 time series for our 2 points. Again, for for the period of about 13 years. And lastly, we are going to do the same and add precipitation data into the system and have a look at the precipitation values for our 2 points. Thank you for watching this presentation on effects of air pollution and climate change on cultural heritage. If you want to leave feedback or have questions, feel free to get in touch. Otherwise, thanks again for watching. Bye bye.